So today's discussion is the first discussion in Chapter 3 on derivatives. The essential question today is, what does the derivative represent? If you remember back to Chapter 2, we had this definition of the slope of a curve at a point. So if we remember, we were saying ignoring the limit that this top here is the rise, the bottom is the run, and then that represented a secant line. And if we close this delta h, if we bring this point back to point P, we get a tangent line. And that was the limit method when we had to take the limit of this expression. That was closing this h gap and bringing the point back to P, and then we have the slope of that tangent line. So Chapter 3, we're going to jump right into the derivative of a function. So the definition of the derivative, if you notice, looks really close to the definition of the slope. There's just one subtle difference, and that is when we talked in Chapter 2 about the slope of a curve at a point, we had a point A. That was a specific location, a specific x value. And now the derivative of a function, we have this generic point x. Okay, so we don't know where we are on the x-axis, but the process is the same. The derivative of a function is the slope of the curve at any point, not a specific point, but any point. So what we're going to end up having is that in Chapter 2, where we ended up getting a number that represented slope, because slope is the steepness of a line, in Chapter 3, we're going to end up getting an expression in terms of x that's going to represent the slope of the function anywhere. And then if we want to know a specific value, we're going to just have to decide where on that curve we want to look at. So when we're talking about a specific point, this is our Chapter 2 limit method. And it literally is the derivative of f at a. In other words, it's the value of the slope. That's what the derivative is. The slope of the function at a specific value, x equals a. Okay, so when I say derivative, you in your mind have to think slope. And so if we want to have a general expression that will work for anywhere on the function, we replace that x equals a with just x. And so we call that the derivative of the function f with respect to x, some x location. And so that, like I said, that's a derivative of f anywhere. And again, when I say derivative, you can just think slope. So when I say it's the derivative of f anywhere, you think it's the slope of f, or the slope of the function anywhere. So when we talk about the derivative, we use this notation called f prime of x. So the function is f of x, the derivative, we just stick a little apostrophe up here, we call it f prime of x. So when we want to write the derivative, we just say f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. And so we have a lot of ways to write the derivative of the function. So here's the function. We can call the function y, or we can call the function f of x. Those are two ways to note the function. So if the function is f of x, the derivative can be written as f prime of x, just like I just got done saying. Or we can call that the derivative of f with respect to x. If we're not using function notation, but we're just using y equals, then we can call the derivative y prime of x. We also can use this notation that says dy dx. So if you think about the definition of the slope of a curve, the limit method, so to speak, that's a rise over run. So dy is the when we use the letter d, it's an incremental y, so it's an incremental rise over an incremental run. And all incremental means it just means a really tiny step. So dy dx, this is literally how we say it phonetically, dy dx. that is a little change in y over a little change in x, so little that we have to use the limit method to find it. So that's another way of noting the derivative, or we could say the derivative of y with respect to x. So the d can stand for derivative. Derivative of y with respect to is kind of the fraction bar x. And then if we want to go back to function notation, we can say df dx. So df dx, there it is phonetically, and the derivative of the function f with respect to x. Or we could use the full function notation, df of x dx. So phonetically that looks like d dx of f of x. So d dx of f of x. So d dx of f of x. So lots of ways to express the derivative. And we'll be using all of these throughout the rest of the course. Okay, so since finding the derivative is using the limit method, so you've actually been finding the derivative at specific points, we're going to go through and look at this this parabola, x squared minus 3. Right? It's a parabola shifted down 3. And we're going to find its derivative. So we're going to notice that when I'm asking you to find the derivative of x squared minus 3, I'm not giving you any point of interest. You know, usually we had an a equals something. In this case, we don't. We're going to find, so we're going to end up with a function that's going to represent the derivative of this function. And then if we want to find a specific point, like what's the derivative when x equals 0, then we can plug in 0 and find specific values. So here's our derivative definition. The f prime of a equals the limit as h approaches to 0 of f of a plus h minus f of a all over h. Now, if we had a specific point, we could go ahead and stick that numeric value in there and do what we did in Chapter 2. But in Chapter 3, we notice we don't have a specific point, so we're replacing the a with an x. So we have the limit as h approaches 0 of the function with x plus h put in here, and then minus the function with x put in here, which we already have, all over h. So notice we're working with the numerator where a is just x. Okay, so let's take a look. Remember, we were always breaking this apart into two pieces. So let's just take a look at this, what goes in this first slot here. So f of x plus h is putting x plus h in right here and squaring it. So x plus h squared minus 3. So when we FOIL this, we get x squared plus 2xh plus h squared minus 3. So foiling this, right, we square this, then we multiply this, x times h, and double it, and then we square that. So don't forget that's the FOIL process right here from algebra, and then minus 3. Notice we can't combine anything here, okay, and that this represents just this first slot right here in the numerator, okay? So now we need this second slot in the numerator. So f of x is just the function itself, x squared minus 3, x squared minus 3, right? Putting x in where x is just going to give us the same thing. So you might notice a few things between these two statements. This statement is going to go here. This statement is going to go here. And if you notice, if we subtract the 2's, the 3's are going to go away, and the x squareds are going to go away. In other words, if you've done your math right, the things that go away, remember we talk about crossing hurdles here, the things that go away, our first hurdle to cross is to get the things that don't have h's to cancel. And so as we put this into the statement, here's our first statement, here's our second statement, and as we distribute this minus sign and drop the brackets, we see that we have our 3's, minus 3 plus 3 going away, and we have our x squareds going away. Okay, so that's our first hurdle. Remember in Chapter 2, our first hurdle to cross was to get those numbers to cancel. And so it's the same first hurdle. If you've done your math right, the numbers cancel, and also the terms without h's cancel. So now we're left with this over this. Okay, so that's that same step from the last screen. So we're going to have everything that cancels go away. We're left with 2x plus h, there it is, and h squared, there it is. So our second hurdle, right, from last chapter was to get the h's to cancel so that we don't have a fraction anymore. So that requires me factoring the top. Remember, we can only cancel factors. So I'm going to factor the top, and there are my h's. So that was hurdle number 2. Our h's are going to cancel, and we're going to be left with this expression. Notice we still have an expression here with x in it. So now we're being asked to take the limit of 2x plus h as h goes to 0. So now it's okay to put 0 in for this. And when we do that, we're left with 2x. Okay, so there's my derivative. My derivative is 2x. That represents the slope anywhere I want to find it. So for instance, here's the 2x is just a line, if you notice. So if you notice, we started with a parabola. That was our function. The derivative ended up being a line. Noticing that pattern is going to be really important as we go into the next couple sections. So I can read values from this line. Okay, when x is 0, y is 0. That means my slope here is 0. So at the vertex of my parabola, I have a horizontal tangent line, right? And horizontal lines have slope of 0. So this, reading the y coordinate off the derivative here, is going to give me that value of that slope. When x is 1, y is 2. So if I go back to my function, when x is 1, if I come down here and put a point on my function, I'm going to have a slope, a tangent line equal to, or a tangent line whose slope is 2. If I come back to my derivative here, when x is 2, y is 4. So I should say y prime is 4. So when I go up to my function and I go up to the value 2, if I would draw that tangent line, its slope would be 4. So that's what this represents. It represents a capability of me being able to find the numeric value of the slope at any x I want throughout that entire function. So a function is differentiable. In other words, we can do this process and find the derivative if it has a derivative everywhere in its domain. So we have to have continuous and smooth functions in order to take the derivative, in order to do that limit method. So continuous and smooth, we have to figure out what that means. Okay, functions on closed intervals must have one-sided derivatives defined at the end of the points. So if we can think about our functions that had domains that begin and ended at specific points, like our piecewise functions. If I want a derivative at the end points, I have to have that closed-in dot. So let's kind of discuss what that means. So here's a function, and if you notice the piecewise function, I have a line from 0 to 1. When x is 0 to x is 1, I have a line. Then from when x is 1 to when x is 4, I have another line. Okay, and then from when x is 4 to x is 6, I have a flat line. And from 6 to 9, I have this line. So it's a piecewise made up of 4 lines. And I don't know what the equations of the lines are, but that's okay, because we know that if I want to find the derivative, all I need to do is find the slope. And so with lines, we have an algebraic way to find the slope. So again, when I say derivative, you just need to think slope. So if I want to find the derivative of this first function here from x equals 0 to x equals 1, all I have to do is find the slope. And since the slope is the same throughout that entire function right here, then I must have the same derivative from 0 to 1. So from 0 to 1, if we calculate the slope, we go right 1 up 2. I have a slope of 2. So there's my slope for this function. Notice that when I have a line, the derivative is a horizontal line. And then what happens in the next section is I have another line. So I can find this slope. I go up 1, right 1, 2, 3. So for the next slope, I have a slope or a derivative of 1/3. And that slope is the same from an x value of 1 to an x value of 4. So I have the slope of a third from an x value of 1 to an x value of 4. And then the next line, I have a slope that's 0. We don't have any rise, so I'm going to record a derivative of 0. And then the last line in my piecewise function, I go down 3, right 3. That's a slope of -1, so that means I have a derivative of -1 all along that function. So here are my derivative values for that piecewise function. And a lot of time piecewise functions, the derivative values are going to abruptly change at these, I'm going to call these corners, okay, these sharp corners here. Derivatives will abruptly change at those locations because we're changing from one function that has a specific slope to another function that has a different slope. So we have to change from one value of the derivative abruptly to a different value of the derivative. So when we're dealing with lines, our derivative graphs, when we're dealing with functions that are lines, our derivative graphs have these steps, so to speak. Let's talk about the endpoints of the functions. So if I'm at the right endpoint, if I have a derivative, then it's going to look like this. And really, I have a derivative at that right endpoint if that dot is filled in. And likewise, at that left-hand derivative, I'm going to have a derivative at that left hand if again, I have that dot that's filled in. So if we go back to this picture, these are filled in dots at 0 and 9. So I have a derivative at 0 of 2, which is the same as the line that's connected to that point. And I have a derivative at 9 of -1, which is the same value as the derivative of the line connected to that point. So these in order to have a derivative at the endpoints, I need to have those dots fill in. I can't have a derivative at these corners here. I can't have a derivative there because I abruptly change values. So notice I have open dots there on my derivative graph. Okay, at 6, I abruptly change from a derivative value or a slope value of 0 to a slope value of -1. So at 6, we don't have a value for the derivative. We have open dots there. So we call those locations, again, corners, and we'll talk a little bit more about that. So as far as smoothness goes, this function, this piecewise function, is not smooth. So we don't have derivatives existing there. So again, at x equals 1, we have a corner. At x equals 4, we have a corner. At x equals 6, we have a corner. So we don't have any derivatives there. So the derivative graph, like I said, it begins to be these flat plateaus. It jumps at those locations. So let's look at this piecewise function. To the left here of 0, we have a parabola, x squared, and to the right we have a line 2x. Okay, so we know we have a sharp corner here. We're gonna call this a cusp though, because it's a curve coming into a line instead of two lines coming together. So we have a sharp cusp here. So again, we won't have a derivative defined at 0 because of that sharp point. But we can use the limit method to find the derivative on the left side. So let's take a look at when a equals 0. And if we look at the directions here, it says show that the following function is continuous but does not have a derivative at 0. So conceptually, we know that we have this sharp point right here. So we know that that's a location where the derivative probably doesn't exist. So let's just verify that. So at a equals 0, this is going back to what we do in chapter 2. We have a specific location. It's 0. We're going to put that in for a. So if we put in 0 plus h into this function, into the parabola, we have 0 plus h squared. If you want to FOIL that, you can, but that's really just h squared. And then f of a, which is f of 0, we put 0 up here. We have 0 squared, which is just 0. So now we have the two things we need to put into the top of the limit method. So here are the two things at the top, h squared minus 0 divided by h. Okay, and then we can simplify that. And then we know that we can cancel in h to get rid of 1 in the bottom. Talking about those hurdles we have to overcome. The constant values go away, we cancel our h, we get the limit as h goes to 0, which is just 0. So we know that the slope as we come into this point on the green function, on the parabola, as we come into 0, the slope is 0, right? It's that vertex of the parabola. So what we have to do then is we have to prove that at this location, the slope here, or the derivative, so to speak, is not 0. It must be some other value. And so we're going to go ahead and use the limit method. But you know when you look at derivative, you got to think slope. And I think you probably already know the slope of this line, so you probably already know the answer you're going to get. But let's go ahead and use the limit method. So we're at 0. We have a point of interest here, so we're using our chapter 2 approach here of the limit method. So 0 plus h, now we're on the blue function, the line, so we're going to put that into here. So we're going to have 2 times 0 plus h, which is 2 times h. So that's that first item in the numerator. Okay, then our f of a is f of 0, so we're going to put 0 in here. 2 times 0 is 0. Oh, that should say 2 times 0 is 0. I copied that over from this, so 2 times 0 is 0. So we have 2h minus 0 over h. So our first hurdle is that the 0 goes away, our constant goes away. Our second hurdle is that we have h's that cancel. And so we have a limit on the blue line, we have a limit that equals 2, which means our slope equals 2. And when I say slope, you can now start thinking derivative. So our derivative is 2. So if we were on the green parabola, our derivative at that point would be 0. If we're on the blue line, our derivative at that point would be 2. So those numbers don't match. So we must not have a derivative at 0. If we have conflicting values, if we have two different values, then we do not define the derivative at that location. So again, we're going to start calling this a cusp because we have a curve coming into a line. So just to summarize here, our essential question, what does the derivative represent? It represents the slope of the curve. It represents what you did in chapter 2, at the end of the chapter in section 4. So again, when I say derivative, you need to start thinking slope. And when functions are continuous, we can find a derivative that represents anywhere on the curve. And when functions are piecewise, then we have to look at those points where the function changes to see if we have that smoothness. So what you can do now is you can start working on your 3-1 derivative of a function day 1 homework in WebAssign. There is a proficiency quiz for 3-1, but I would wait until we're done with day 2 to take that if you feel like you want to take the proficiency quiz instead.